Hello there, and welcome. Tonight we're going to explore one of the most mind-bending ideas in all of science, the multiverse. So get comfortable, relax, and let your mind wander as we journey through these fascinating concepts together. There's no need to remember every detail or follow every twist and turn. Just let the ideas wash over you as we contemplate the profound question of whether our universe is the only one, or if there might be countless others out there, existing alongside ours in ways we can barely imagine. This is a topic that invites contemplation rather than intense focus. The multiverse isn't like gravity or evolution, things we can test and observe directly. It's more speculative, sitting at the edge of what we currently understand about reality. Some scientists find the idea compelling, others are skeptical, and many are somewhere in between. But regardless of where you stand, the multiverse theory raises fascinating questions about the nature of existence itself, questions that are perfect for pondering as you drift and relax. But before we begin, please take a moment to like and subscribe, but only if you enjoy what I'm doing here. Also, leave in the comments where you're tuning in from and what time it is there. It's great to see how these videos connect people from around the world. Now get comfortable and let's begin. So let's start at the beginning, taking our time as we explore. What exactly do we mean when we talk about the multiverse? What is the multiverse? The multiverse, in its simplest form, is the idea that our universe, everything we can see and measure, might be just one universe among many. These other universes, if they exist, could be fundamentally different from ours. They might have different laws of physics, different constants of nature, or even different dimensions. Some might be similar to ours, while others could be so alien that life as we know it couldn't possibly exist there. Think about it this way. For most of human history, we thought Earth was the center of everything. Then we discovered Earth orbits the Sun. Then we found out the Sun is just one star among hundreds of billions in our galaxy. Then we learned our galaxy is one of trillions in the observable universe. The multiverse theory suggests we might need to take one more step. Our entire universe might be just one among an enormous, perhaps infinite, collection of universes. It's a humbling thought, isn't it? But where does this idea come from? Is it just wild speculation, or is there something more to it? The origins of multiverse. Thinking. The concept of multiple universes isn't entirely new. Philosophers have played with similar ideas for centuries, wondering whether there might be other worlds beyond our own. But the scientific discussion of the multiverse really began to take shape in the 20th century, as physicists developed new theories about how the universe works. One of the key developments came from quantum mechanics, the branch of physics that deals with the behavior of matter and energy at the smallest scales. Quantum mechanics revealed that the subatomic world doesn't behave like the everyday world we're familiar with. Particles can exist in multiple states at once, and the act of measuring something can actually change its properties. This strange behavior led some physicists to wonder whether reality itself might be more complex than we thought. Another major development came from cosmology, the study of the universe as a whole. In the early 20th century, astronomers discovered that the universe is expanding. If you run the clock backward, everything was once compressed into an incredibly hot, dense state. This led to the Big Bang theory, which describes how the universe began about 13.8 billion years ago. But as scientists studied the Big Bang more carefully, they encountered puzzles that the standard theory couldn't easily explain. Some of these puzzles led researchers to propose new ideas, and some of those ideas naturally suggested the existence of multiple universes. So the multiverse isn't just one theory, it's actually a family of related ideas, each arising from different areas of physics. Let's look at some of the main versions of the multiverse theory that scientists have proposed. the quantum many-worlds interpretation. Let's start with one of the strangest versions of the multiverse, which comes from quantum mechanics itself. It's called the many-worlds interpretation, and it was first proposed by physicist Hugh Everett in 1957. To understand this idea, we need to talk about what makes quantum mechanics so weird. At the quantum level, particles don't have definite properties until you measure them. An electron, for example, doesn't have a specific location until you observe it. Instead, it exists in what's called a superposition, a kind of fuzzy state where it's in multiple places at once. The mathematics of quantum mechanics describes all these possible states using something called a wave function. Here's where it gets interesting. In the standard interpretation of quantum mechanics, when you measure the electron, the wave function collapses. All those possibilities suddenly reduce to one actual outcome. But this collapse is mysterious. What causes it? Why does measurement change things? Everett proposed a radical solution. What if the wave function never collapses? What if, instead, every possible outcome actually happens, but in different branches of reality? In this view, when you measure that electron, the universe splits. In one branch, you find the electron in one location. In another branch, you find it somewhere else. Both versions of you are real, existing in parallel universes that can never interact with each other. Does this sound crazy? It probably does. But here's the thing. The many worlds interpretation doesn't add anything to the mathematics of quantum mechanics. It's simply taking the equations seriously and following them to their logical conclusion. The wave function describes all possible outcomes, and in the many worlds view, all those outcomes are real. Now, you might be wondering, if the universe splits every time a quantum measurement happens, and quantum events are happening everywhere all the time, doesn't that mean the universe is splitting into an unimaginably vast number of branches every single instant? Yes, that's exactly what this interpretation suggests. Every quantum event, from a photon being absorbed by your eye to a particle decay in a distant star, creates new branches. The number of parallel universes would be constantly growing, becoming more and more enormous. To many people, this seems extravagant. Do we really need to believe in countless parallel universes just to explain quantum mechanics? Some physicists find the many worlds interpretation elegant because it doesn't require the mysterious collapse of the wave function. Others find it hard to accept because these parallel universes are, by definition, unobservable. We can never directly confirm they exist because we can never visit them or communicate with them. But let's move on to another version of the multiverse, one that comes from a very different area of physics. The inflationary multiverse. This version of the multiverse arises from our understanding of the Big Bang and what happened in the earliest moments of the universe. To understand it, we need to talk about cosmic inflation. Back in the 1980s, physicists were puzzling over some strange features of the universe. For one thing, the universe looks remarkably uniform. When we observe the cosmic microwave background radiation, which is the afterglow of the Big Bang, it has almost exactly the same temperature in every direction. But according to the standard Big Bang theory, regions on opposite sides of the sky were never close enough to exchange energy and reach the same temperature. So why are they so similar? To solve this and other puzzles, physicist Alan Guth proposed the theory of cosmic inflation. The idea is that in the first tiny fraction of a second after the Big Bang, the universe underwent a period of incredibly rapid expansion. We're talking about an expansion so fast that the universe doubled in size not once, but dozens of times, all in a span shorter than a blink of an eye. This rapid expansion would have smoothed out any irregularities and explains why the universe looks so uniform today. Inflation has become widely accepted because it explains several puzzling observations. But here's where things get interesting for the multiverse. Many versions of inflation theory suggest that inflation doesn't happen everywhere at once. Instead, It happens in separate regions, and each region becomes its own universe, expanding and cooling, and eventually forming galaxies and stars. Think of it like a pot of boiling water. Bubbles form in different places at different times. In the inflationary multiverse picture, our universe is like one of those bubbles. Inflation stopped here, allowing matter and energy to condense and form the structures we see around us. But in the larger space beyond, inflation might still be happening, and new bubble universes might be constantly forming. This is sometimes called the eternal inflation scenario, because inflation never truly ends. It keeps happening in some regions, even as other regions cool off and become universes like ours. The result would be a vast, perhaps infinite, multiverse filled with bubble universes, each one potentially having different properties. And here's something remarkable. These different universes might not all have the same laws of physics. The fundamental constants of nature, things like the strength of gravity or the mass of an electron, might vary from one bubble to another. We'll come back to this idea later because it has profound implications. The inflationary multiverse is intriguing because it arises naturally from a theory, cosmic inflation, that was developed to solve real problems in cosmology. Scientists didn't set out to create a multiverse theory. The multiverse just seemed to fall out of the mathematics when they tried to understand the very early universe. But there's yet another version of the multiverse we need to discuss, and it's based on an even more fundamental question. Why does our universe have the properties it does? The landscape multiverse and string theory. This brings us to string theory and what physicists call the landscape multiverse. To understand this, we need to step back and ask a basic question. Why does nature follow the laws it does? Think about the fundamental constants of nature. The speed of light, the strength of the electromagnetic force, the mass of the proton. These are all numbers that we measure, but they could, in principle, have been different. Why do they have the specific values we observe? For a long time, physicists hoped we might find a theory of everything, a single, elegant set of equations that would explain all the forces and particles in nature. Many thought these equations would also explain why the constants have their particular values. There would be one unique solution, one way the universe could be. String theory seemed promising as a candidate for this theory of everything. The basic idea of string theory is that the fundamental building blocks of nature aren't point-like particles, but tiny, vibrating strings of energy. Different vibration patterns correspond to different particles. It's an elegant idea, and for a while physicists hoped it might provide that unique solution they were looking for. But as string theorists worked out the mathematics, they discovered something unexpected. String theory doesn't give one unique solution. Instead, there are an enormous number of possible solutions, each corresponding to a different way that extra dimensions could be curled up. And we're not talking about dozens or thousands of solutions. Estimates suggest there might be 10 to the power of 500 different possible configurations. That's a number so large, it's hard even to comprehend. Each of these solutions would correspond to a universe with different properties, different particle masses, different force strengths. This vast collection of possibilities is called the string theory landscape. And here's where it connects to the multiverse. If eternal inflation is real, and if string theory is correct, then perhaps all these different possible universes actually exist. Each bubble universe in the inflationary multiverse might correspond to a different point on the string theory landscape. This is speculative, of course. String theory itself hasn't been confirmed, and the landscape picture is controversial even among string theorists. But it raises an interesting possibility. Rather than explaining why our universe has its particular properties, maybe we should accept that all possible properties are realized somewhere in the multiverse. Our universe simply happens to be one with properties that allow for stars, planets, and ultimately life. This leads us to one of the most important arguments for the multiverse, something called the fine-tuning problem. Let's explore that next. The fine-tuning problem. One of the most striking features of our universe is that it seems remarkably well suited for life. If you change certain fundamental constants by even a tiny amount, the universe would be completely different, and life as we know it couldn't exist. Consider the strength of gravity. If gravity were slightly stronger, stars would burn through their fuel much faster, giving planets less time for life to develop. If it were weaker, stars might not form at all, or they might not burn hot enough to forge the heavy elements necessary for life. The range of values that allows for a universe with long-lived stars and complex chemistry is actually quite narrow. Or think about the cosmological constant, a number that affects how fast the universe expands. If this constant were significantly larger, the universe would have expanded so rapidly that galaxies and stars never formed. Matter would have been spread too thin. Again, the observed value seems to be in a narrow range that allows for structure formation. There are many such examples. The mass of the electron, the difference between the mass of the proton and neutron, the strength of the nuclear forces, all of these seem to be finely tuned. Change them even slightly, and you get a universe that's either empty or filled with black holes or devoid of the chemical complexity needed for life. This is the fine-tuning problem. Why does our universe have properties that allow for life? There are essentially three possible answers that scientists have considered. The first is pure chance. Maybe the constants just happen to have the values they do, and we shouldn't be surprised we're here to observe them. After all, if they were different, we wouldn't exist to ask the question. This is sometimes called the weak anthropic principle, and while it's logically correct, many scientists find it unsatisfying. It seems like an incredible coincidence. The second possibility is design. Maybe the universe was intentionally set up with these particular values by some kind of creator or designer. This isn't a scientific explanation in the usual sense because it doesn't make testable predictions, but it's certainly an option that some people find compelling for philosophical or religious reasons. The third possibility is the multiverse. If there are countless universes with different properties, then it's not surprising that at least some of them, including ours, would have the right conditions for life. We find ourselves in one of these hospitable universes simply because that's the only kind of universe where observers can exist. This is sometimes called the strong anthropic principle in the context of a multiverse. From this perspective, the multiverse provides an explanation for fine-tuning without requiring design or accepting extraordinary coincidence. The laws and constants aren't the same everywhere across the multiverse. They vary, and we inhabit a region where they happen to be right for life. Does this settle the matter? Not quite. The multiverse explanation for fine-tuning is controversial. Some scientists find it compelling, others think it's giving up on finding a deeper explanation. And there's a philosophical question lurking here. Is the multiverse really a scientific theory if we can never observe these other universes? Let's tackle that question head on. Can we ever prove the multiverse exists? This is one of the biggest challenges facing the multiverse theory. In science, we typically confirm theories by making predictions and testing them through observations or experiments. But by definition, other universes in the multiverse are beyond our reach. We can't visit them, we can't see them, and we can't directly measure their properties. So how could we ever prove they exist? Some philosophers and scientists argue that this makes the multiverse unscientific. If a hypothesis can't be tested, they say, it's not really science, it's metaphysics. It might be an interesting idea, but it doesn't belong in the same category as theories like relativity or evolution, which make specific, testable predictions. But defenders of the multiverse argue that this criticism is too simplistic. They point out that we often believe in things we can't directly observe. We believe in quarks inside protons, even though we can never isolate a single quark. We believe in the interior of the sun, even though we can't go there. We accept these things because they're part of theories that do make testable predictions. Similarly, the multiverse might emerge as a consequence of theories that we can test. Take cosmic inflation, for example. Inflation makes predictions about the universe we can observe, like patterns in the cosmic microwave background radiation. These predictions have been confirmed by observations. If the best version of inflation theory also implies eternal inflation and a multiverse, should we reject the multiverse just because we can't observe other universes directly? There's another point to consider. While we might not be able to observe other universes directly, we might find indirect evidence. For instance, if another bubble universe collided with ours in the distant past, it might have left an imprint, a kind of bruise in the cosmic microwave background. Some scientists have looked for such signatures, though so far nothing conclusive has been found. There's also the possibility that the constants of nature might reveal patterns that only make sense in a multiverse context. If we could measure enough constants and find they cluster in certain ways, that might be evidence they're drawn from a larger distribution across a multiverse. But let's be honest, these indirect tests are challenging, and the evidence, if it exists, is subtle. For now, the multiverse remains a theoretical possibility rather than an established fact. It's a consequence of some of our best theories, but it hasn't been proven. This brings us to an important question. What do scientists actually think about the multiverse? The scientific debate. The scientific community is genuinely divided on the multiverse. You'll find respected physicists on both sides of the debate, and the arguments can get quite heated. Supporters of the multiverse argue that it emerges naturally from well-established theories like inflation and quantum mechanics. They point to the fine-tuning problem and argue that the multiverse offers the best explanation. Some even suggest that refusing to accept the multiverse is like refusing to accept that the Earth orbits the Sun just because we can't feel the motion. The evidence is there in the mathematics of our theories, they say, and we should follow where it leads. Critics, on the other hand, raise several concerns. One major criticism is that the multiverse can be used to explain almost anything, which makes it unscientific. If any possible universe exists somewhere in the multiverse, then we can't use the multiverse to make specific predictions. Whatever we observe, we can always say, well, this is just the universe we happen to be in. This lack of predictive power troubles many scientists. Another criticism is that the multiverse seems extravagant. It multiplies entities beyond necessity, as philosophers would say. If we can find another explanation for fine-tuning or quantum mechanics that doesn't require infinite other universes, wouldn't that be better? Many scientists believe we should keep searching for such explanations rather than accepting the multiverse. There's also a concern about giving up too easily. Some scientists worry that invoking the multiverse means giving up on the goal of finding a deeper theory that explains why the constants have their particular values. Instead of explaining why our universe is the way it is, we're just saying all possibilities exist somewhere. To some, this feels like admitting defeat. On the other side, multiverse proponents argue that the critics are holding on to old expectations that might not apply to the deepest questions about reality. Maybe there isn't a deeper explanation for why the constants have their values. Maybe the multiverse is the answer, even if it's not the tidy, elegant answer we might have hoped for. The debate continues, and it's not clear when or how it will be resolved. But regardless of whether the multiverse is real, thinking about it has led to interesting developments in physics and cosmology. It's pushed scientists to think more carefully about what it means for a theory to be testable, and it's opened up new areas of research. Now let's consider some of the different types of multiverses that have been proposed. We've already discussed a few, but there are others worth mentioning. The many levels of the multiverse cosmologist Max Tegmark has proposed a helpful way to organize different multiverse ideas. He suggests there are 4 levels of multiverse, each more exotic than the last. Level 1 is the simplest. If space is infinite, as many cosmologists believe, then there could be regions of space so far away that light from them hasn't reached us yet. These regions would be beyond our observable universe. And if space is truly infinite, then somewhere out there, purely by chance, there would be regions identical to ours. Same galaxies, same planets, even copies of you. This isn't really a multiverse in the exotic sense. It's just the consequence of having infinite space and a finite number of possible arrangements of matter. Level 2 is the inflationary multiverse we discussed earlier. This is where different bubble universes form from eternal inflation, each potentially with different physical constants and laws. Level 3 is the quantum many-worlds interpretation. Every quantum measurement creates branches of reality, leading to an enormous tree of parallel universes. Level 4 is the most speculative. Tegmark proposes that every mathematically consistent set of physical laws corresponds to an actual universe. In this view, not only do universes with different constants exist, but universes with completely different mathematical structures, different numbers of dimensions, even different logics. If it can be described mathematically, it exists somewhere. This 4th level is so speculative that even many multiverse proponents are skeptical, but it illustrates how far these ideas can be pushed. Each level asks us to expand our conception of reality in a different way. What's interesting is that these different levels are largely independent. You could believe in the quantum many-worlds multiverse without believing in eternal inflation, or vice versa. The evidence and arguments for each are different. Let's shift gears a bit and ask a different kind of question. If the multiverse is real, what would that mean for us? How would it change our understanding of our place in reality? Philosophical implications. The multiverse has profound philosophical implications. If it's real, it transforms our understanding of concepts like existence, uniqueness, and even identity. Consider existence itself. In a single universe, things either exist or they don't. But in a multiverse, especially one like Tegmark's Level 4, almost anything you can imagine exists somewhere. Every possible variation of history, every conceivable form of life, every story you can think of might be playing out in some universe. What does it mean for something to exist if everything possible exists somewhere? Or think about uniqueness. We often value things because they're one of a kind. But in certain versions of the multiverse, particularly the infinite Level 1 multiverse, there would be copies of everything, including you. Not just similar people, but exact duplicates living lives identical to yours. Does that change the meaning or value of your experiences? Then there's the question of probability and likelihood. In a single universe, we can talk about whether something is likely or unlikely to happen. But in a multiverse where everything possible happens somewhere, how do we make sense of probability? If all outcomes occur in different branches or different bubbles, what does it mean to say one outcome is more likely than another? These aren't just abstract philosophical puzzles. They touch on questions that matter to us personally. If every choice you could make is made in some branch of the quantum multiverse, does that change your sense of free will or moral responsibility? If every possible version of history plays out somewhere, does that affect how we should think about the significance of events in our own universe? Different people answer these questions differently, and philosophers are still debating them. Some argue that, even if the multiverse is real, it doesn't diminish the meaning of our experiences. After all, you only experience this particular version of reality, and that's what matters to you. The fact that other versions exist elsewhere doesn't make your life any less real or significant. Others find the multiverse unsettling, precisely because it suggests that nothing is unique. Every triumph, Every tragedy, every moment of beauty or horror is repeated endlessly across the multiverse. To some, this is depressing. To others, it's oddly comforting. There's no single right answer to how we should feel about these implications. Let's consider another angle on this. How does the multiverse relate to some of the biggest questions in cosmology and physics? The multiverse and the big questions. The multiverse intersects with several of the deepest questions in science. One of these is the nature of time itself. In a single universe with a beginning and possibly an end, time has a clear direction. There's a past, a present, and a future. But in an eternally inflating multiverse, time becomes more complicated. While time moves forward within our bubble universe, the larger multiverse has no clear beginning or end. Inflation has been happening eternally in the past and will continue eternally in the future. Different bubble universes are created at different times, but there's no universal now that applies across the entire multiverse. This raises puzzling questions. If inflation is eternal into the past, does that mean the multiverse has always existed? If so, what does that mean for the concept of a beginning? Some physicists have argued that even eternal inflation must have had a beginning, while others think the question might not even make sense in the context of quantum gravity. Another deep question is the nature of mathematics and physical law. Why does mathematics work so well to describe the universe? Why do we find elegant mathematical patterns underlying physical phenomena? In a single universe, this is a profound mystery. But in Tegmark's Level 4 multiverse, where every mathematical structure corresponds to a universe, the connection between math and physics becomes almost tautological. Physical laws are mathematical structures, and mathematical structures are just different possible universes. Whether you find this satisfying or circular probably depends on your philosophical inclinations, but it's an interesting way to think about the relationship between abstract mathematics and concrete physical reality. There's also the question of why there's something rather than nothing. This might be the deepest question of all. In a single universe, we have to explain why the universe exists at all. Why is there anything? But in some versions of the multiverse, particularly Tegmark's Level 4, the question might dissolve. If all possible mathematical structures exist, then nothingness is just one of those possibilities. Why, hey, no more fundamental than anything else. Existence becomes the default, not the mystery. Again, whether this really answers the question or just rephrases it is debatable. But the multiverse offers a different perspective on these ancient philosophical puzzles. Now you might be wondering, are there any practical implications of the multiverse? Does it matter for anything beyond abstract theory? Does the multiverse have practical implications? This is a fair question. If we can never visit other universes, or even observe them directly, does the multiverse theory have any practical value? In the immediate sense, the answer is probably no. Believing in the multiverse won't help you build better technology or cure diseases. But in a broader sense, the multiverse discussions have already had some practical impacts on how science is done. For one thing, thinking about the multiverse has forced physicists to clarify what makes a theory scientific. What does it mean to test a theory? Can we accept consequences of theories even if those consequences are unobservable? These methodological questions affect how physicists approach all kinds of problems, not just the multiverse. The multiverse has also influenced research directions. The search for patterns in the cosmic microwave background that might indicate collisions with other bubble universes is a real research program. Scientists have developed specific methods to look for these signals. Even if nothing is found, the attempt has led to better analysis techniques that are useful for other cosmological studies. Furthermore, inflation theory, which suggests a multiverse, has become a major focus of research. Physicists are constantly refining inflationary models and working out their predictions. This work has improved our understanding of the very early universe, which in turn connects to particle physics and our understanding of fundamental forces. There's another, more subtle point. Science advances by exploring ideas, even speculative ones. Some of the most important breakthroughs in physics came from people who were willing to think about seemingly absurd possibilities. The multiverse might turn out to be wrong, but thinking about it might lead scientists to discover something unexpected. And let's not forget the cultural impact. The multiverse has captured public imagination in a way that many scientific ideas don't. It appears in movies, TV shows, and books. It gets people thinking about the nature of reality and the limits of what we can know. That sense of wonder and curiosity is valuable in itself. But now, let's address some of the specific objections that critics have raised. What are the strongest arguments against the multiverse? The case against the multiverse, critics of the multiverse have raised a number of serious objections, and it's worth considering them carefully. One of the strongest criticisms is the problem of unfalsifiability. As we mentioned earlier, if other universes are unobservable in principle, then the multiverse hypothesis can't be tested directly. And if a hypothesis can't be tested, many philosophers of science argue it's not really a scientific claim. It might be an interesting metaphysical speculation, but it doesn't belong in the same category as testable theories. Defenders respond that the multiverse is a consequence of testable theories like inflation, but critics counter that we should be cautious about accepting consequences that go beyond what we can verify. Maybe our theories are wrong or incomplete in ways that would eliminate the multiverse implications. Why should we believe in unobservable entities just because they appear in our current theories? Another objection concerns the explanatory power of the multiverse. Some critics argue that the multiverse doesn't really explain anything. It just pushes the mystery back a level. Instead of asking, why does our universe have these particular properties? We're now asking, why does the multiverse exist? We haven't eliminated the need for explanation. We've just made the thing that needs explaining bigger and more complicated. Related to this is the problem of measure. In an infinite multiverse with all possible properties represented, how do we calculate probabilities? If there are infinitely many universes with observers like us, and infinitely many with slightly different properties, how do we make sense of why we observe what we do? Mathematically, comparing infinities is tricky, and some critics argue that the multiverse leads to paradoxes or ambiguities that make it impossible to extract meaningful predictions. There's also a concern about scientific conservatism and simplicity. Science usually prefers simpler explanations over more complex ones, all else being equal. A single universe is simpler than a multiverse with countless universes. Unless the evidence strongly demands a multiverse, critics argue, we should stick with the simpler hypothesis. Some critics also worry about the cultural impact of the multiverse. They suggest that multiverse thinking encourages a kind of anything goes attitude where speculation replaces rigorous evidence. If physicists can invoke unobservable universes to explain away puzzles, what's to stop similar reasoning in other areas? Critics fear this could lower standards in physics. Finally, there's a practical concern. Physics has limited resources, limited funding, limited brilliant minds to tackle problems. If many physicists spend their careers working on untestable multiverse theories, are we wasting resources that could be spent on research with more tangible payoffs? These are serious objections, and multiverse proponents take them seriously. The debate continues with good points on both sides. Now let's look at some specific versions of the multiverse and how they relate to current physics research. Recent developments in multiverse research. While the multiverse remains speculative, research related to it continues. Let's look at some recent developments. In observational cosmology, scientists continue to analyze data from satellites and telescopes that measure the cosmic microwave background. They're looking for anomalies that might hint at collisions between our bubble universe and others. The Planck satellite, which operated from 2009 to 2013, provided the most detailed measurements yet of the cosmic microwave background. Some researchers have claimed to find patterns that might be evidence of bubble collisions, but these claims remain controversial and haven't been confirmed. In theoretical physics, researchers are exploring different versions of inflation theory. Some inflationary models naturally lead to a multiverse, while others don't. By working out the detailed predictions of these models and comparing them to observations, scientists hope to narrow down which versions of inflation are most likely correct. If versions that imply a multiverse turn out to fit the data better, that would be indirect support for the multiverse, even if we can never observe other universes directly. String theory research also continues, though string theory itself remains unconfirmed. String theorists are working to understand the landscape of possible solutions better. If the landscape picture is correct, it would provide a framework for thinking about how different bubble universes might have different properties. Some researchers are investigating whether there might be ways to test string theory, predictions about our own universe, which would indirectly provide evidence about whether the landscape picture makes sense. In quantum information theory, scientists are exploring the implications of the many worlds interpretation. Some researchers argue that quantum computing, which relies on superposition and entanglement, might provide new ways to think about whether parallel branches of reality exist. While this doesn't prove the many worlds interpretation, it might eventually provide indirect evidence, or at least make the interpretation more concrete and testable. There's also ongoing philosophical work on what it would mean for the multiverse to be true, and how we should think about evidence and confirmation for theories with unobservable consequences. Philosophers of science are examining whether the multiverse really is unfalsifiable, or whether there might be subtle ways to confirm or disconfirm it. All of this work is ongoing, and it's too early to say what conclusions will emerge. But the multiverse isn't just idle speculation. It's connected to active research programs in multiple fields. Let's take a moment to consider how the multiverse relates to another major unsolved problem in physics: the nature of dark matter and dark energy. The multiverse, dark matter and dark energy. Our universe is mostly made of things we don't understand. Regular matter, the stuff that makes up stars, planets, and us, accounts for only about 5% of the total mass and energy in the universe. About 27% is dark matter, which we can detect through its gravitational effects, but which doesn't emit light. And about 68% is dark energy, a mysterious force that's causing the expansion of the universe to accelerate. We don't know what dark matter or dark energy actually are. They're among the biggest mysteries in contemporary cosmology. So how does this relate to the multiverse? One connection is through the cosmological constant, which is related to dark energy. The cosmological constant represents the energy density of empty space itself. Quantum field theory predicts that empty space should have energy, but when physicists calculate how much, they get an answer that's wrong by an enormous factor, maybe 120 orders of magnitude. This is sometimes called the worst prediction in physics. Yet observations tell us that dark energy exists and has a small but non-zero value. Why is it so small compared to what theory predicts, but not zero? This is a fine-tuning problem. In a single universe, the value of the cosmological constant seems like an absurd coincidence. But in a multiverse with different values in different bubbles, we would naturally find ourselves in a universe where the cosmological constant is small enough to allow for galaxies and life. If it were much larger, the universe would have expanded too quickly for structures to form. This is actually one of the more compelling applications of multiverse reasoning to explain a specific observed feature of our universe. It doesn't prove the multiverse exists, but it does show how multiverse thinking can address real puzzles in cosmology. As for dark matter, the situation is different. Dark matter seems to be some kind of particle that interacts only weakly with regular matter. Physicists have proposed many candidates for what dark matter might be, and experiments are actively searching for it. The existence of dark matter doesn't obviously connect to multiverse ideas in the same way the cosmological constant does. But if dark matter particles are eventually discovered, understanding their properties might provide clues about the fundamental structure of physics, which could in turn relate to whether multiverse theories make sense. The point is that the biggest mysteries in cosmology, including dark matter and dark energy, are connected to the same deep questions about fundamental physics that lead to multiverse theories. Solving one puzzle might shed light on the others. Now let's consider a different angle. What would life be like in other universes if they exist? Life in other universes. This is where speculation really takes off, but it's fun to think about. If other universes exist with different physical laws or constants, what would they be like? Could life exist there? In most universes, the answer is probably no. If you randomly change the constants of nature, you almost always get a universe that's either boring or chaotic. Many universes would expand so quickly that matter never clumps together. Others might collapse back on themselves almost immediately. Some might have only one kind of particle. Others might have forces so strong or so weak that atoms can't form. The conditions necessary for life, at least life as we know it, are quite specific. You need long-lived stars to provide energy. You need planets where complex chemistry can occur. You need elements heavier than hydrogen and helium, which means you need stars that can forge these elements and then explode to scatter them into space. All of this requires a delicate balance of physical constants, but in an infinite multiverse there would presumably be some universes where life is possible, even if they're rare. Some of these life-bearing universes might be quite similar to ours. Others could be radically different. Could there be universes where life is based on different chemistry, where information is stored in something other than DNA, where organisms use exotic energy sources? In principle, yes, if the physical laws allow it, but it's hard to say what forms this life might take, because we only have one example of life, our own. There's an even more intriguing possibility. What if some universes have different numbers of spatial dimensions? We live in a three-dimensional universe, not counting time as the fourth dimension. But some physics theories suggest that other dimensionalities might be possible. Could life exist in a two-dimensional universe, or a four-dimensional one? 2 dimensions might be too restrictive. It's hard to see how you could have the complexity necessary for life in 2 dimensions. Complex networks and structures tend to require 3 dimensions. But what about 4 or more dimensions? Some physicists have speculated about this. The mathematics gets complicated, but it's possible that 4-dimensional universes could be stable and allow for complexity. What would it be like to be a 4-dimensional creature? We can't really visualize it, but mathematically we can study it. Of course, all of this is extremely speculative. We have no evidence that any of these other universes exist, let alone that they contain life. But the multiverse idea naturally leads us to ask these questions, and that in itself is intellectually stimulating. Let's bring things back down to earth and ask a more personal question. How should we, as individuals, think about the multiverse? Should we believe in the multiverse? This is ultimately a personal question, and there's no single right answer. The multiverse is at the frontier of science, where evidence is sparse and arguments are complex. Reasonable people can disagree. If you value scientific conservatism, you might be skeptical of the multiverse. You might prefer to wait for more concrete evidence before accepting such an extraordinary claim. After all, the multiverse implies that reality is vastly larger and stranger than we can directly observe. That's a big leap to take based on indirect theoretical arguments. On the other hand, if you're impressed by how naturally the multiverse arises from theories like inflation and quantum mechanics, you might find it plausible. You might think that following the mathematics of our best theories is the right approach, even when it leads to surprising conclusions. In this view, the multiverse isn't an add-on to physics. It's a prediction that emerges when we take our theories seriously. There's also a middle ground. You can think the multiverse is an interesting possibility without committing to believing it's real. You can appreciate the intellectual challenge it presents and the questions it raises, while remaining agnostic about whether other universes actually exist. What you shouldn't do, probably, is let the multiverse change how you live your day-to-day life. Even if other universes exist, you still only experience this one. Your choices and actions still matter in this universe. The meaning and value you find in life don't depend on whether there are other versions of you elsewhere. In fact, some people find the multiverse inspiring precisely because it highlights how unique our existence is, even if other universes exist. The fact that we find ourselves in a universe where stars shine, where chemistry allows for life, where consciousness is possible, these are remarkable facts regardless of whether other universes exist, where these things aren't true. So should you believe in the multiverse? That's up to you. What's important is understanding the arguments on both sides and appreciating the deep questions the multiverse raises about the nature of reality. Let's explore one more aspect of this topic, the multiverse in popular culture and how it differs from the scientific concept. The multiverse in fiction versus science. The multiverse has become a popular concept in movies, TV shows, comics, and books. Superhero movies often feature alternate timelines and parallel universes. Science fiction stories explore what-if scenarios where history took a different turn. But it's important to understand that the multiverse of fiction is usually quite different from what scientists are discussing. In fiction, characters often travel between parallel universes. They might meet alternate versions of themselves, or change events in one universe while being aware of another. This makes for great storytelling, but it's not what the scientific multiverse theories suggest. In the quantum many-worlds interpretation, for instance, the different branches can't interact after they split. You can't visit another branch or communicate with your other selves. The branches are completely separate. They exist in a mathematical sense, as part of the universal wave function, but there's no way to travel between them. Similarly, in the inflationary multiverse, different bubble universes are separated by regions of space that are still inflating. These regions are expanding so fast that nothing, not even light, could cross from one bubble to another. The bubble universes are fundamentally isolated from each other, so the dramatic scenarios you see in movies, where characters hop between universes or where changes in one universe affect another, are not part of the scientific multiverse theories. They're fictional devices that make for entertaining stories, but they shouldn't be confused with what physicists are actually proposing. That said, the popularity of multiverse stories in fiction reflects a genuine fascination with these ideas. People are intrigued by the possibility that reality might be bigger and stranger than it appears. Fiction allows us to explore these ideas in imaginative ways, even if those ways aren't scientifically accurate. And who knows? Maybe some aspects of fictional multiverses will inspire new scientific ideas. Science and fiction have often influenced each other throughout history. Just because something is fictional now doesn't mean it will always remain so. Now, as we approach the end of our exploration, let's take a step back and consider the big picture. What does the multiverse debate tell us about science itself? What the multiverse tells us about science. The multiverse debate reveals something important about how science works, especially at its frontiers. Science is often portrayed as a straightforward process. You make observations, form hypotheses, test them, and gradually build up knowledge. And for many areas of science, this picture is accurate. But at the cutting edge, things get more complicated. When we're dealing with questions about the fundamental nature of reality, direct observation becomes difficult or impossible. We can't run experiments on the universe as a whole. We can't rewind the Big Bang and watch it happen again, with different settings. So we have to rely more heavily on mathematics and theory, extrapolating from what we can observe to what we can't. This creates a dilemma. On one hand, we want to follow our theories wherever they lead, trusting in the mathematics that has been so successful in describing nature. On the other hand, we want to maintain empirical grounding and not drift into pure speculation. The multiverse debate is essentially about where to draw the line. How much weight should we give to theoretical elegance and mathematical consistency? How much should we demand direct observational confirmation? These questions don't have easy answers, and different scientists make different judgments. What's important is that the debate is happening openly. Scientists are arguing, critiquing each other's ideas, and trying to clarify what standards should apply. This is how science makes progress, even when dealing with questions that push the boundaries of what's testable. The multiverse also reminds us that science is a human endeavour. Scientists have different temperaments and philosophical inclinations. Some are bold speculators, willing to follow ideas to their extreme conclusions. Others are cautious empiricists, demanding proof before accepting extraordinary claims. Both types of scientists are valuable. The tension between them keeps science healthy and prevents it from becoming either too reckless or too timid. Finally, the multiverse debate shows us that the biggest questions, the ones about why the universe exists and what reality fundamentally is, remain open. Despite all our scientific progress, we're still grappling with mysteries that humans have wondered about for thousands of years. That's humbling, but it's also exciting. There's still so much we don't know, so much left to discover. Wrapping up our journey. So where does all this leave us? Is the multiverse real? The honest answer is, we don't know. The multiverse is a serious scientific hypothesis, emerging from respected theories in physics and cosmology. But it hasn't been proven, and it faces significant challenges, both theoretical and observational. What we can say is that the multiverse is a natural consequence of some of our current best theories. If inflation is correct in certain forms, a multiverse seems to follow. If the quantum wave function is the complete description of reality and never collapses, the many worlds interpretation suggests countless parallel branches. If string theory is right and has a vast landscape of solutions, perhaps all those solutions are realized somewhere. But each of these ifs is substantial. Inflation might need modification. Quantum mechanics might require an interpretation that doesn't involve multiple worlds. String theory might be wrong, or might turn out not to imply a multiverse after all. The evidence for the multiverse is indirect, emerging from the mathematics of theories rather than from direct observation. For some scientists, this is enough. The theories work well to describe what we can observe, and if those theories imply a multiverse, we should accept it. For others, the lack of direct evidence is a serious problem. They want to see the other universes, or at least see unambiguous traces they've left behind before believing. What's remarkable is that we're even having this conversation. A century ago, we barely understood that there were other galaxies beyond our own. Now we're seriously discussing the possibility that our entire universe, with its hundreds of billions of galaxies, might be just one bubble in an infinite sea of universes. Whether the multiverse is real or not, Thinking about it has expanded our understanding of what's possible. It's forced us to question assumptions, to think more carefully about the relationship between mathematics and reality, and to grapple with the limits of what we can know. The multiverse represents both the power and the limits of human understanding. It's a product of our remarkable ability to use mathematics and logic to reason about things far beyond our direct experience. But it also reminds us that there may be aspects of reality that are forever beyond our reach, truths we can infer but never fully confirm. In the end, perhaps the most important thing isn't whether the multiverse is real, but that we're asking the question at all. The fact that we can wonder about the fundamental nature of reality, that we can construct theories and arguments about what might exist beyond what we can see, that's itself remarkable. We live in a universe, or multiverse, that's capable of producing beings who can ask these questions. Whether there are other universes or not, that's something worth marveling at. The cosmos has given rise to consciousness, to curiosity, to the human capacity for wonder. And that's true regardless of how many universes exist. So tonight, as you look up at the stars, you might ask yourself, am I looking at the only universe, or just one of many? Are there other versions of me out there looking up at different skies? Is reality a single unique thing, or an infinite collection of possibilities, all made real? We may never know for certain, but we can keep searching, keep thinking, keep pushing the boundaries of what we understand. That's what humans do. That's what makes us who we are. The multiverse theory asks us to imagine that reality is far stranger and far grander than we ever thought. Whether it's true or not, that invitation to expand our imagination, to think bigger, to question what we think we know, that's valuable in itself. Thank you for joining me on this journey to the edge of knowledge and perhaps beyond. The question of whether our universe is one of many remains open, a puzzle for future generations to solve. But in asking the question, in trying to peer beyond the limits of what we can see, we're participating in one of humanity's greatest adventures, the quest to understand the nature of reality itself. And who knows, maybe someday in this universe or another, we'll find the answer. Until then, we can keep wondering, keep exploring, and keep asking, what if?